In this video, we introduce transaction management and look at a couple examples. A transaction is defined as a set of SQL statements or just one SQL statement submitted by a user, meaning someone running SSMS or some other client, or submitted through an end user application such as a website or a desktop application, and that action does something to the database such as creating an object, deleting an object, or updating an object. Typically the object is data in a table, but it could be any other object in the database such as a user object or even a login or a database object. We think of transactions as logical units of work. We develop our code in increments of transactions, and we execute our code as a transaction, and we think of the entire process of doing something with a computer as a set of transactions that get executed interspersed with non-database things like screen updates. This is certainly a database-centric view of this entire universe. The transaction generally exists to protect itself from other transactions. If transactions become interleaved, then data gets corrupted, and our data is a mess, and our system is useless. To prevent that from happening, a transaction will lock or hide or shelter some information in the database, which is typically a row in a table, a set of rows in a table called a page, or an entire table. The more granularity required by a transaction, the slower the transaction will run, and the slower in general the entire database will run, meaning if you have to lock individual rows, you will slow down processing a little bit rather than locking entire pages. But on the other hand, if you lock an entire page or you lock an entire table, you may prevent other transactions from doing things that they should otherwise be able to do. So there is a trade-off between granularity of locks, and that is way beyond the scope of this discussion, so we won't get into any details here. We use the word consistency to mean when the transaction is finished, it will allow only data in a valid state to be written to the database. That means that fields match all the constraints applied to the relevant tables. If there is a foreign key required, then that foreign key is present, and things like that. But interestingly enough, inside the transaction, between the begin and the commit, the database may be in an inconsistent state. That's not a problem for us because no one else outside the transaction can see that inconsistency, so we're not causing anybody else any grief. Only two things can happen when you run a transaction, and one of them is good. The transaction may succeed, meaning all the row updates and deletes and inserts will be committed to the database, and everyone else using the database will be able to see them. Or the transaction could fail, and the database engine rolls back or undoes all of the operations in the transaction, and that again removes the inconsistency from the intermediate values that were created in that transaction. So we have success, we have failure, we have no middle ground. We either succeed or we don't. State transition diagram for a transaction. It's going to spend most of its time being active. that is executing all of the statements inside the transaction. When we get to the commit phase, we are considered to be partially committed until we are fully committed. Anytime during that partially committed phase, something could go wrong. There could be a read error, the network could go down, there could be a violation of a table constraint, there could be an inconsistency detected in a foreign key. The logic in the transaction itself could initiate a failure with a rollback. So any of those conditions may cause us to go from partially committed to failed, and then eventually to aborted, which means the condition is completely wiped from memory. If nothing goes wrong, we go from partially committed to committed, and we're done. So the transaction can only have one of two final states, success or failure. Success we refer to as committed, failure we refer to as aborted. Here's an interview question for you. You probably will be asked at some point in your career to explain the concept of ACID, A-C-I-D. It is an acronym describing the behavior of a database relative to transactions. We say that a database is ACID if it is atomic, consistent, isolated, and durable when dealing with transactions. The A in ACID stands for atomic, meaning that the whole transaction runs or none of the transaction runs. We don't get half of a transaction committed and the other half aborted. That's impossible. The C in ACID stands for consistency. When the transaction finishes, the database must be in a consistent state. That means that if the database is not in a consistent state when a commit is executed, then the transaction is aborted or rolled back by the database manager. So we are depending on SQL Server to verify that we're in a consistent state when we attempt to commit. During the transaction, between the begin and the commit, we are isolated from the other people using the database. So there may be hundreds or thousands of customers adding records, updating records, running reports, generating screens and PDFs and downloads. None of those other transactions have any idea what's going on inside of our transaction because we are isolated from the rest of the world. The A in ACID stands for isolated. The D in ACID stands for durable, meaning that when we commit, we can't lose those commits because something went wrong after the fact. Now that usually involves a transaction log or some other backup strategy so that we can recover the changes made by that transaction if that becomes necessary. Here's our very basic syntax for manipulating transactions. We mark a starting point. We delimit the beginning of a transaction with begin or begin tran or begin transaction. I usually use begin tran. We can create save points if necessary with the word save followed by the keyword tran or transaction followed by the name of the save point. We commit a transaction to the database with the word commit, and we abort or roll back the current transaction with the rollback command. We can also roll back to a save point. Save points are a little complex for us. We will not be addressing them in this presentation. If you type in one line of SQL in the query window, or you submit one line of SQL to the database engine through a program or an application that you write, that one line is considered to be a transaction. So we call that auto commit. Individual lines of SQL not wrapped in a begin and a save or a begin and a rollback are considered individual transactions. If you'd like to follow along, grab a copy of the AP database creation script from Blackboard or whatever LMS we happen to be using at the time. Check local listings. Log in as yourself and begin. Run the script after you change the using statement to your particular database. You may have already done this in a previous exercise, and that's fine. Let's look at an application of the theory we've been discussing. In the AP database, we have a very common structure where there is a master table or a parent table and a detail table, which may be referred to as a child table. So we have master, detail, or parent-child table structures. This particular one will be dealing with invoices. There is a table called invoices, and that is the parent or master table. There is a table called invoice line items. That is the child or detail table. This is a real-world scenario where you create an invoice with an invoice header, a customer name, a date, payment terms, other things relevant to an invoice, and then you fill out the body of that invoice with individual line items of the things that are being billed for. Therefore, a particular invoice may have multiple invoice line items because you usually bill for more than one thing or more than one event on an individual invoice. From the perspective of a database, the master table or the invoice has a foreign key relationship with the detail table or invoice line items. In order to implement this in a script, which could be a stored procedure, we add the master record first to the invoices table, then we add the detail records to the line items table, but we need the foreign key in order to do that. We cannot add rows to the child table without the primary key of the master table to use as a foreign key. Now, before we get there, let's just briefly touch on the identity variable. The identity variable is a system variable that will always give us the most recently created identity value regardless of the scope. So if there are other scripts running or there's other code that you've written, be very careful using the identity variable because you may not get the scope that you think you're getting. But it does exist, and if you're careful, you can make use of it. Now, we are more interested in, skipping ahead 2 slides, the scope identity function, which gives us the identity value in the current scope. So we're going to use that because it gives us more granularity and it's a safer bet than the identity variable. Now I'm going to skip back a slide because I just threw this in to illustrate what happens if you don't have an identity data type set in your table definition. Here's a table called city, and you don't have to worry about the table, you don't have to create it, but you can see from the slide the arrow points to the fact that the identity specification is set to no. There is no identity variable in this table. There's a primary key called city. There's a city ID which is set to an int. So this table isn't following our design standards, and one of the dramatic upshots of that is when you try to use the identity variable, it's not possible because there is no identity value set in the table definition for that table. So we're kind of nudging you towards using identity variables, and we're just giving you another reason why that's a good idea. Back to this invoice parent-child scenario again. We can write an insert statement that writes a row into the invoices table. Then in the next line of code, we can extract the scope identity value from that previous insert, store that in a variable called invoice ID, and use that in our subsequent insert operations into the line items table. This is how we get the primary key from the parent table and use it as the foreign key in the child table. So you are welcome to grab this code. And I am going to use a temporary copy of the AP database called AP1, but you would be working in your private student database if you want to do this exercise. And when we run this, we get one row affected 3 times. The first instance of one row affected in the message window is from the insert operation into the parent table. And the second 2 one row affected messages are from the 2 insert operations into the child tables. And it might be interesting to print out that value of that variable that we stored scope identity into. When we run this again, then mine prints 118, meaning that there were already 117 rows in the table, or we'd already used the first 117 primary keys in that invoices table. Then when I run it again, I should get 119, 120. Each time you run this little script, it adds a new row to the invoice table, creating a new primary key in that invoice table. And then if you were to take a look at the line items table, I'll just grab the top 1,000 rows of that and scroll all the way to the bottom. You would see 2 rows for each of those primary keys that you just added through the script. So the scope underscore identity function gives us the last identity value that was used in an operation. And we don't want to take any chances with this. We want to put our call to scope identity immediately after that insert operation. And we also want to store it somewhere. So let's not be referencing scope identity in different locations in the code. Let's grab a copy of the scope identity, store it into a variable, and not have to worry about whether we have the one that we think we have, or if we accidentally put in another insert and we got a different value from a different insert operation. What I don't want you to do then is I don't want you to embed scope identity calls into these insert statements. Rather, use that variable that we captured the value into. Because in a simple case like this, it will work, but right here it's going to fail miserably, because the second call to scope identity in this second insert into the line items table is going to give us the value of the last identity stored in the previous insert into the line items table. So this highlighted piece of code here, this scope identity call embedded into this second insert into invoice line items, will be disastrous. It won't give us the primary key of the invoices row that we inserted up above. It will give us the primary key of the invoice line items row that we inserted in the preceding statement. Don't get sloppy with the scope identity calls. Call it once immediately after you do the insert and store a copy of it in a local variable, and you'll have much less trouble. Let's wrap some begin and end transaction syntax around this code that we've been discussing. If we don't wrap the begin and the commit, or the begin and the rollback properly, we're going to get some kind of error like this. And I throw this in just to show you what you can do to cause yourself real grief if you're not paying attention. In this example, I am attempting to delete all the rows from the city table. I write delete from T-City. Doesn't matter what's in T-City. That's not an issue here. And then after I do the delete, I immediately do a rollback. Well, there is no explicit transaction to be rolled back. But the delete's already been done because, as we saw earlier, an individual statement is auto-commit, and the delete statement was considered its own transaction, so it auto-committed, it ran, and by the time we got to the attempt to roll back, there was nothing to roll back. You can see at the bottom of the screen we got an error. The rollback transaction request has no corresponding begin transaction, and that's really, really bad because all the rows in our city table are now gone. So be careful that you have a begin if you attempt or you plan to use a rollback. Alright, so referring back to that slide we saw earlier with the invoice master and child relationship, I've taken the same code, but I've wrapped a begin and an end. A begin and a commit around it. And the beauty of this now is that if something goes wrong in those three insert statements, the commit will not run and the catch block will run, and inside the catch block is a rollback. So we've made our code a lot more robust and a lot more fail-safe because a lot of things could go wrong in this little tiny script. We may successfully insert a row into the invoices table. We may successfully capture the scope identity value of that last primary key inserted into the invoices table. And then the insert into the child table, the invoice line items table, could fail miserably because that table is corrupt or there is a constraint error of some kind. And we have to find a way to back out of this. We don't want the parent row added to the invoices table if the child rows cannot be successfully added to the invoice line items table. Therefore, all of these inserts have to run or we roll back the transaction. Again, we want our transaction to be atomic. We want to sleep well at night knowing that there will be no invoice records without corresponding line item records. Here's another trick we can play. I'm sorry, not really a trick, a useful tool is the row count variable, which provides us a count of the number of rows affected or impacted or created by the previous SQL statement, edit, update, delete, insert, whatever. So in this case, I'm attempting to update a table called the employee table in the human resources schema, and I'm setting the job title to executive based on some where clause. The particulars aren't really necessary, but if I did not update any rows, if row count is 0, if the update didn't do anything, then I'm going to print a warning. Now, printing a warning might not be the best way to handle errors, but you can extrapolate that into some reasonable error handling. The point is, the row count is a very handy way to know if we actually did anything in the previous SQL statement. Here's another application of row count. I've wrapped this in a transaction. My strategy here is that I don't want to delete more than one invoice. And this is pretty slick because I can roll back this transaction and undelete invoice rows from the invoices table. So they're not really gone until I execute the commit. It's kind of a control Z as long as you're inside the transaction. It's kind of an undo. What I'm doing here then is I execute delete invoices where vendor ID equals 34. and then I immediately check the row count. I want to know how many rows I deleted from the invoices table. If the row count's greater than 1, then for whatever reason I decide that's a problem. There should only be one invoice in this table from vendor ID 34. So the row count is greater than 1. I immediately roll back the transaction. I print a message that says more invoices than expected, deletions rolled back, and I drop out of the transaction. If the row count was not greater than 1, if the row count was 0 or 1, I execute a commit and print a confirmation message. The logic or the intent isn't really germane to us, but the structure of this and the strategy for using a row count is important. When do you use transactions? Well, we'd like to say use them all the time, but we'd also like to say keep them as small as possible. So don't wrap your entire database logic in one big humongous transaction. That just defeats the purpose of having a multi-user database. One rule of thumb is if you have 2 or more action queries, update, insert, delete, that are hitting data, and if the first action query fails, you do not want to execute the second action query. You'll have to think about what kind of scenarios that might be. So that's the time to use a transaction. If the first query fails, you roll back the transaction and you do not execute the second query. This is kind of a subset. When you're updating foreign key references, which is essentially the same as the previous slide, which would mean we're doing an update on a table. We've done something to the parent table and we need to go in and change the primary key on the child table, which is essentially running 2 update queries on 2 different tables, and that would be an excellent time to use a transaction. Remember, as we're talking about this, that the transaction is locking rows or groups of rows or entire tables. So this is great and it works for us, but we don't want to go locking things if we don't have to. That's why it's important to think about when to use a transaction explicitly and perhaps when not to. Here's another instance when you should use a transaction explicitly: when you're copying or moving groups of rows from one table to another. Remember, a move operation is really going to be 2 steps. You're going to copy a set of rows from one table to another, and then you're going to go back and delete those rows from the original table. That's 2 steps. That's at least 2 SQL statements. If the first one succeeds, but the second one fails, you need to roll back the first one. If the first one fails, you don't even want to try to execute the second one. Another good time to use an explicit transaction is when you've built a select statement and you're writing into a table variable or a temporary variable or a temporary table in your script, and then you're processing that temporary table to do some kind of action on another table. So you may read a list of vendors that are in Ohio. Then you may go through and update all of the invoices from all of those vendors to change the sales tax. Well, if the update to all of the vendors and all of the invoices fails, then you have a problem. But in this case, if the select statement goes stale or gets corrupted or something bad happens to it, then you need to roll back what you already did, and this is a time to use a transaction. And here's a general reason to use a transaction: if anything that you could do could potentially corrupt database integrity, meaning delete some foreign keys or violate some constraints, then you need to be able to roll back that transaction. So you should wrap that code in a begin and a commit to give you that capability. Let's look at a case study. And we've all used the eBay. We've all bid on things. Let's assume there is an item, and for the sake of simplicity, let's assume it has no bids. And we are looking at a situation where bidder one, someone on their computer somewhere in the world, enters a bid of $1, considers carefully their options, rechecks the quality of the item, reads the reviews, clicks bid. While that bid is being processed on the server side on the eBay computer, another person has entered $2 and clicked bid. Now it is crucial that the first bid is processed completely before the second bid is processed. And that is a prime candidate for setting up a couple of transactions to make sure that bidder 1 is completely processed before bidder 2 even starts to process. This situation is called a race condition because if the order of processing gets interleaved or the two sets of steps begin to race, then the results are no longer deterministic and your database is worthless. Let's broadly define the set of steps that we need to process a bidder. Let's say that step A is to lock a record in a table called current bid and write the current bid value into that table. And step B is to lock a record in the current high bidder table and write the ID of the current high bidder into that table. Then let's say that bidder 1 is going to execute steps A and B, and bidder 2 is going to execute steps A and B. And actually these are executed on the eBay server. They're not executed by the bidder. The bidder has simply clicked bid and then holds their breath until they win. But there are 2 steps to process bidder 1, 2 steps to process bidder 2. These steps cannot interleave, else we have a disaster. We must process them in a specific order to get the results that we need written into those tables. Here are the steps that must be performed and the order in which they must be performed. We have to have B1A, B1B, followed by B2A, B2B. That means that the current bid table and the current high bidder table must be updated for bidder 1 completely and committed to the database before we can update the current bid for bidder 2 and the current high bidder for bidder 2. B1A, B1B, B2A, B2B must be the order of steps that we perform. Without transactions, though, we are not guaranteed this is the order of operations that's going to happen. What happens if the steps are performed in the order B1A, B2A, B1B, B2B? So I encourage you to grab a piece of paper or your favorite writing utensil and work out on paper what the database would look like, what would be stored in that database if we executed step B1A, which executed the bid, which updated the bid amount, followed by B2A, which updated the bid amount again, and then B1B, and then B2B, or rearrange the steps in any order except the required order and see all the possibilities that we could end up with. It's very easy to get inconsistent results, essentially a corrupted database, if we don't have the transactions constructed properly. To solve this problem, we implement transactions. We wrap a begin tran and a commit around This should be B1A here, my mistake. We wrap a begin and a commit around the B1 steps, the bidder 1 steps. We commit those steps. Then we wrap a begin, tran, and a commit around the B2 steps, and we commit those steps. That ensures that the B1 steps will not run, will run before the B2 steps. And remember, the reason this transaction cannot begin is because the previous transaction has locked components of tables, and the second transaction knows that it cannot start. So there's a lot going on here behind the scenes that we really don't know about, but the SQL Server database engine has locked parts of the database which prevent the second transaction from beginning until the first one is finished. We've essentially serialized this logic. We've ensured that whichever transaction begins first will get to finish before the second transaction begins. Now, this kind of thing is difficult to demonstrate because transactions run so quickly unless they're very long and overcomplicated for our purposes. So if you do a little internet searching, you end up on Stack Overflow and you find out that there is a wait for command that you can use in SQL to delay execution of a script. You can tell your script to wait 5 seconds, wait 10 seconds, I think wait up to 24 hours. And we don't do this in the real world because we don't time our scripts. We don't build in execution delays on purpose. But we do use this for demonstration purposes when we want to demonstrate race conditions. So take a look at the link that I provided at the bottom of the slide. Read about wait for a little bit. Look at the Microsoft documentation for it and get a feel for what it does and how you can use it. I can take my pseudocode that I demonstrated on a previous slide, and in the first transaction, the first set of code for bidder 1, I can jam in a delay and then immediately start the set of instructions for bidder 2, and that will effectively interleave the set of steps. So I can have the first step of bidder 1 executed, I can drop into a delay, then I can start the steps for bidder 2, and after that delay finishes, the second step in bidder 1 will finish, and I've got an interleaved mess that completely corrupts the data in my database. As an exercise then, I encourage you to look at what I've got written here on the slide and determine what the order of steps would be given that this delay has been put in place. So you can assume that the steps run very quickly, but the delay between B1A and B1B gives plenty of time for B2A and B2B to run. So we've interleaved or merged or melded these two scripts together because they're not in transactions. What if you put these in transactions? Again, as a thought experiment, think about wrapping a begin tran and a commit around this little bit of code. What effect would that have when I executed that code and then immediately jumped into another window and tried to execute this code? Well, the second set of code would not be able to run because the begin tran and the commit would lock the resources necessary for that first set of code to run, and until those resources were unlocked, until we ran the commit, the second set of code in the other window wouldn't be able to start. So the database engine is pretty smart, and it knows what resources are necessary inside of a transaction and what resources need to be locked in order for that transaction to run in an isolated environment.